When testing a hypothesis, we often have to write a couple of very pesky sentences at the end and draw a conclusion and that sort of thing. There are two sentences, and this is not about how to do all the math to get there. This is about how to use the math to draw a pretty picture and then to get those two sentences right every single time. All those sentences with the drop-down menus and the is, not, support, reject, fail to reject, reject. We don't know. But we will know by the end of this because we will be able to draw a pretty picture. Your first step is to identify the claim. That could be your null hypothesis or your alternative hypothesis. Now, I'm supposed to say null hypothesis and alternative hypothesis, but referring to the null hypothesis as ho and the alternative hypothesis as ha amuse me, so from henceforth, they shall be known as ho and ha. Next, you do some math. I will show math on screen, but this video is not about doing the math nor the technology to do the math. It is about drawing pretty pictures, which leads me to your third step. You're going to draw a pretty picture. And then after you draw the picture, you're going to give one sentence that is exclusively about your ho, and then a second sentence that is about your claim. Here's a great page to screenshot. So the very first thing you're going to need to do is identify if you have a ho or a ha, and the way you do that is identify if your claim has an equal to or it doesn't have an equal to in it. For example, if your claim says something like is at most, then that means that mu is less than or equal to. Well, the or equal to means that it's going to be part of a ho, and its complement would be the ha, that is the mu is greater than. So they will always have a this much stuff and the rest of it kind of situation. If your claim is something is not something, then that means that your mu is not equal to, so that's a ha. Your claim would be your ha, and the ho would be that mu is equal to. So they'll always go in complement pairs like that. So your ho always has an equals somewhere in it, and your ha always doesn't have an equals in it somewhere. So the next thing that you're going to do is you're going to find your critical value. That's going to be your z naught, and your critical value is going to be defined by where your rejection region is, and that's going to be listed as your alpha. Now you can identify where your rejection region is based on the ha. It doesn't matter what the claim is, you'll always be able to identify where your rejection region is based on the ha. So when mu is greater than, you have a right-tailed test. When mu is not equal to, you have a two-tailed test. Now we're splitting the rejection region over both tails. And if your mu is less than, then that means that you have a left-tailed test. So we're going to identify where the rejection region is, and then how far does it go? That's going to be how you use your z naught. So your critical value is going to be how far your alpha goes. And so we're going to put our z naught in first, and then we can see to color our alpha in. Now, the other thing that you're going to need is a standardized test statistic, which is your z, that's based on your sample. And so your sample mean is that x bar that's in there minus mu divided by your CLT, which these should all be familiar things to you. Sometimes they ask you for a p-value, and your p-value is going to be an area that is bounded by your z. I will show you with pretty pictures what I mean next. For the sake of clarity and for pretty pictures, then I'm going to draw a bell curve that's red. I'm going to draw a rejection region, or I'm going to show you my alpha that's green, but my alpha is only going to come into play after I find my critical value. So, and I can move my critical value around. It could be any of these kinds of things. My alpha is defined by my critical value. So we're going to plot the z naught first, and then after that, then we can color in our rejection region, which is going to be the size of that alpha. Now, after I have that information, then we're going to find our standardized test statistic, which is a z. And just like that, I can move these things around. We're going to have big conversations about whether or not the z is inside the rejection region like this, or whether or not it's outside the rejection region like this. Sometimes we are expected to find a p-value, and the p-value is bounded by that z, the same way that alpha is bounded by z naught. So when I move my z around, then my p-value gets bigger or smaller, because alpha represents an area, and then the p-value also represents an area, but my alpha is the area that's my level of significance that came from my original problem, and my p-value is the area that is bounded by the standardized test statistic that I found. So sometimes we're just going to talk about, is the p bigger than the rejection region or smaller than the rejection region? And sometimes we're going to talk about, is the z outside the rejection region or inside the rejection region? And it's the same information. When we write a conclusion, then the first sentence is always about the ho. If your standardized test statistic is inside the rejection region, then we're going to say that we reject the hoe. And if it is not in the rejection region, then we're going to fail to reject the hoe. The first sentence is always about the hoe. It does not matter what the claim is. The second sentence is always about the claim. So then we say at a whatever the alpha percentage level of significance, then there, and then now if it's inside the rejection region, we say there is enough evidence, and if it's not, then we say there is not enough evidence. So it's just a, is the dot inside or outside the rejection region? Is your p-value more stuff or not as much stuff as the rejection region? And then is there either is or is not enough evidence to, now the next part depends on whether or not your claim is the hoe or the ha. If it's the hoe, then there is or is not enough evidence to reject, and if it is the ha, then there is or is not enough evidence to support the claim that, and then you just copy and paste the claim. So ho is always about reject when you're talking about the second sentence, and ha is always about support. So we can always identify whether or not we say is or is not based on whether the standardized test statistic, the z, is the dot inside the rejection region or not inside the rejection region. And we can also identify, if we're going to use the word reject or support, whether or not the claim was the ho or the ha. The first thing is to plot your bell curve. That would go right there. The second thing is to plot z naught, which is 1.645, so that would be right around there. The next thing is to shade in the rejection region. So that right there is your alpha. Notice how your alpha is bounded by your z naught. That area is connected to where that critical value is. And then the next thing would be to label your standardized test statistic, which is z. So there's your z right there. And then that may be enough information, because we could say that z is inside the rejection region, and then we have all the information we need, but sometimes you're expected to find a p-value. The p-value is just the area that is bounded by z. So that would be this, and the p-value is smaller than alpha, which is going to be useful in the conclusion that we want to make. So either you can say that your z is inside the rejection region, or your p-value is smaller than your alpha. So here's my bell curve. Now my alpha is going to be split over both tails because it's a two-tailed test. We know this because we had a ho and ha equal not equal to situation. So I have a z naught there, but the symmetric negative one is over there. And my alpha, color in your rejection region, right there. And then we're going to look at where the z is. And oh, it's so tiny over there. And so then when we color it in, I promise it's purple. If you want a p-value, then it's really, really, really tiny. So it looks like the z has not escaped out of the rejection region, and the p is not going to be bigger than alpha.